I'm going to be a sixth grader by the end of this quarter. You wait. All right, so this time we're going to talk about force and impulse. So this is bringing together all of the things we've learned about vectors, all of the things we've learned about momentum, and finally talking about changes in momentum. It's not that interesting when things just go in a straight line forever. I want to know what happens when they interact. So I want to start off by outlining what force and impulse are, and then I'm going to do a kind of involved problem with them so we can get a little bit of hands-on experience. Okay, so my intuition for these two things, force and impulse, I want to give first. So force, I think of as, force F, I think of as telling me about how the objects that I'm interested in are either speeding up or slowing down over time. So it tells me about how they're speeding up or slowing down over time. Impulse just tells me change in momentum from one time to another. So both force and impulse are vector quantities. Both force and impulse are vector quantities. Force has the units of newtons. 1 Newton, capital N, which is the same as a kilogram times meter per second squared. And since impulse is just change in momentum, it also just has the same units as momentum. So that's a kilogram meter per second. Kilogram times meter per second. Okay, so explicitly, force is mass times acceleration. So force is mass times acceleration. It's the rate of change of velocity scaled by mass. So basically, again, that just tells me that force changes speeds. If I have a force like gravity that pulls me downward, gravity tends to change my speed downward unless there's another force to balance it out. Similarly, impulse is just basically representing this change in momentum. There's nothing fancy about it. The interesting thing that links them is that the change in momentum is equal to the impulse, right? Which is the same as the average force times some change in time. Average net force times the change in time. So if I'm looking at 2 points in time, say maybe before I get on that ledge and after I get off that ledge, and I think about the force that I must have exerted on the ledge in order to change my momentum from left to right, there was some average force that I exerted over that time interval to change my momentum. If I wanted to know the average force I exerted, I could find the average force by taking the change in momentum, or the impulse, and dividing it by the change in time. That's one to probably hold on to as well. Okay, a little bit of like vocab hygiene here. So I want to talk about splitting up the universe, partitioning the world into system and environment, kind of like back in 7a. So forces interact over lots of different scales. So, me and you are both affected by like the sun's gravity, right? We have lots of different forces acting on us. We've also got lots of forces inside of us. So you've got, the forces that hold your cells together. You've got the forces that caused fluids to flow. So when we talk about forces inside a system, like forces acting between objects of the same system, we call those forces internal forces. If there's an outside force that's acting on your system, we call that an external force. So gravity is a common external force on a system. If I have like a balloon, that's not a balloon. If I have a balloon full of gas particles, the gas particles in that balloon have a bunch of internal interactions. They have a bunch of internal forces that cause them to like bounce against each other, bounce against the walls, etc. But they've also got an external force in the form of gravity. Where I draw that boundary between external and internal is kind of up to me, or like kind of up to the problem. So so I want to get us used to that mindset of saying, what should I include in my system to make it so that forces are manageable, so I know what's going on? If there are no net forces acting on a system, so maybe my balloon's out in space, if there are no net forces acting on my system, so here like no gravity, for example, net external forces, then we say that the system is closed. It's closed when there are no net external forces, and it's open when there are net external forces. All right. Last thing I want to mention here, I've kind of been doing it already, but if we have some objects or set of objects that we're considering, and we want to draw the forces on them kind of on the same diagram, we call all of these individual forces force vectors, and we call this diagram that I've drawn here the free body diagram. It's a free body diagram in the sense that it's a bunch of bodies, and the force vectors are free to be, places other than the origin. So I just draw the vectors kind of wherever they belong, on whichever components of my system they belong. All right, so to try to make this concrete, I want to give an example with some numbers. So what I want us to imagine for a second is that I've got two asteroids. I'm going to make the first asteroid. Here we go. I'm going to make the first asteroid 10 kilograms, let's say. And it'll run into another asteroid that is, let's call it 20 kilograms. I want to say that initially the asteroid on the right is moving at a speed of 10 meters per second, and the asteroid on the left is moving at a speed of, I don't know, let's call it 5 meters per second. Okay, and let's say that this is my initial state here, and let's say that at the end, here we go, the 10 kilogram asteroid is moving to the left at a speed of let's call it 6 meters per second. Will that work? Yeah, I think that'll work. 6 meters per second. Okay, cool. So what I'm going to do is I'm only going to consider, for the moment, the 10 kilogram asteroid as my system. All right? So what I want to do now is think about how momentum changes. And what I'm going to ask as my end result question is, if the two asteroids interacted for 0.3 seconds when they hit each other, what was the average force over this interval? Okay, and to answer this question, I'm going to introduce one more construct we'll use in 7b, which is the momentum chart. So the momentum chart is laid out like this. I've got some initial momentum, P initial. I've got some change in momentum, and I've got some final momentum. Okay, so the deal is that the initial momentum, and these are all vectors, hang on, the initial momentum plus the change in momentum, or the impulse, is the final momentum, right? Hopefully that makes sense, because delta P is defined as final minus initial. So if I were to rearrange this, I would get, delta P equals P final minus the initial. Okay, so I'm only considering the 10 kilogram asteroid as my system. So that's what I'll consider in my chart. My question is, what was the average force over the interval? So in order to get at force, I'll need the impulse over time. That's delta P over delta T, the change in momentum over time. I know the change in time. They interacted for 0.3 seconds. So that's the time interval over which the force acted. Now, what about this change in momentum? Well, I'm going to have to solve back for it. So I've got the initial and final momenta. Initially, I have a 10 kilogram object moving 5 meters per second to the right. So this is 10 times 5 to the right. That's 50 kilogram meters per second to the right. And at the end, I'm moving 6 meters per second to the left. So that's 10 times 6, which is 60 kilogram meters per second to the left. Okay, left. Now, what's the change? What do I need to add to a rightward pointing vector to make it point left? I'm going to need to add a large leftward pointing vector. And how big does it need to be? It's going to need to be pretty big. So let's do this explicitly. I'll do it as explicitly as possible. So the initial momentum plus the change in momentum is the final momentum, which means the change in momentum, the thing that we need in order to find the force, the change in momentum is going to be final minus initial. The initial momentum, if I just look at it again, hang on, it's going to the right. So it's going to be, there's no vertical component to it. I can write it like this. The initial momentum is 50, 0 with the appropriate units. The final momentum is going to be 60, negative 60, 0, because it's moving leftward, negative 60, 0. So final minus initial here is going to be negative 60, 0, minus 50, 0, which means that the change in momentum was negative 110, 0. Whoa. Okay, so intuition check. Does it point left? It does. So this green vector plus this red vector should yield me this light blue vector. If I add them head to tail, just visually, I can kind of verify that. So there's my initial momentum. If I add head to tail my change of momentum, I'll get, drawing from my origin here, I'll get my blue vector. Nice. So there's a one-dimensional example of how momentum might change for the asteroid. Now, I've got my change in momentum. I've got my delta p is negative 110, 0 kilogram meters per second. To get my force, I have to divide that change in momentum by the time interval. So force average is going to be delta p over delta t, which is going to be, what did I say, 0.3 seconds? 0.3 seconds. So the average force is going to be negative 110, 0 over 0.3 seconds, which is going to have units of, this is going to have units of newtons, right? Because it's going to be a kilogram meter per second per second. Kilogram meter per second squared, that's a newton. And what do I get out? I get negative 366, 0 newtons. So force is pointing in the same direction as change of momentum here. It's pointing left, and that's its average magnitude. That's how much force was exerted over this collision. Cool. Over the course of the collision, I should say. So this description of the way that force and change of momentum are related, that is Newton's second law. What I want to do in the last part of this video is talk about Newton's third law. And I can bring it back to this example down here with the asteroid. It's going to be really cool. Check it out. So Newton's third law tells us that for every force exerted, there's an equal and opposite reaction force. So in this case, when the 10 kilogram asteroid hits the 20 kilogram asteroid, a force is exerted on the 10 kilogram asteroid and by the 10 kilogram asteroid. So one force acts on the 10 kilogram asteroid and pushes it away. The other force acts on the 20 kilogram asteroid and acts in the opposite direction. And as we'll see in just a moment, they must be equal in order for momentum to be conserved. So check it out. The initial total momentum of my system, so let's now consider the whole thing to be my system. The initial total momentum is what? Well, if I look at the left asteroid, I'm going to call this one left and this one right. If I look at the momentum of my left asteroid, the momentum of my left asteroid is 10 times 5. That's in the x direction. So 50, 0. There's nothing vertical here. And the momentum of the right asteroid, initially, is, let's see, 20 times 10 makes 200. Negative 200, 0. Negative because it's moving to the left toward decreasing x. Okay, so the total initial momentum, total, is going to be just the sum of those two. That's going to be negative 150, 0. All right, let's consider the final scenario. So in the final scenario, I calculated before that the final momentum for the left asteroid, is going to be negative 60, 0, with the appropriate units, kilogram meters per second. And because there are no external forces acting on the system, total momentum should be conserved. So the initial total momentum is the same as the final total momentum. So in other words, I know that Pf total, which is P left final, plus P right final, the sum of their two individual momenta, that's still got to be the same thing it was before, negative 150, comma 0. Okay, so what's the final momentum of my right asteroid? What's that? I've got this first term as negative 60, comma 0, plus the right asteroid final is negative 150, comma 0. So that tells me that the right asteroid now has a momentum of, at the end, has a momentum of negative 150 minus negative 60 makes negative 90, comma 0 kilogram meters per second. So it's still moving to the left, but it's moving to the left slightly slower than it was before. Originally, it was moving negative 200, so to speak. It had a momentum of negative 200. Now it has a momentum of negative 90. So it's going to be moving more slowly. Okay, so the change in momentum, we're getting close now, bear with me. The change in momentum of the right asteroid is final minus initial. I should put vectors on all of these, sorry. Minus the initial momentum of the right asteroid. And that's going to be negative 90, comma 0 minus negative 200, comma 0, which is, let's see, that's 110, right? Double check me here. Yeah, 110, comma 0. Okay, notice anything different? Notice anything strange? This this 110, this change in momentum is the same as the change in momentum it's same in magnitude at least. It's the same in magnitude as the change in momentum we observed for the other asteroid. So it's got the same like amount of impulse. J is the same for either asteroid. So yeah, so the force of the 10 kilogram asteroid on the 20 kilogram asteroid will be the same but in opposite directions. So the force of 10 on 20 is just going to be the change in momentum of the right asteroid, delta P R, over delta T, which is again 110, comma 0 over 0.3. It is 366.6, comma 0 newtons. In other words, it is an equal and opposite force. It's the same size, but it points in the opposite direction. So if I were to put that on a free body diagram, at the moment of collision, here's what I'd see. I would see my 10 kilogram asteroid and my 20 kilogram asteroid, and there's a force acting on the 20 kilogram asteroid that is the same exact size as the force acting on my 10 kilogram asteroid. These both have length 366 newtons. So 366, comma 0, and this should be newtons, and negative 366, comma 0. Equal and opposite forces. Okay, I think that about does it for this video. In the last video, we will talk through some intuition builders and wrap up for the night. Thanks for hanging out.